Welcome to GK Tricks India. I am Saghnik and today we are going to have a small discussion on the chemistry of alkenes. Today we will discuss about the structure, its bonding, and the few properties of alkenes which separate them and make a distinct class of organic compounds. Right? So coming to the alkenes, what comes to your mind when I talk about alkenes? The simplest one. Talking about the simplest one, we have methane. Here, as you can see, it has one carbon attached to 4 different hydrogen atoms. Here, and 4 different hydrogen atoms, and it is often represented by the chemical formula CH4. Right? It's a very commonly known gas, which is often found in the marsh areas and often used as a fuel, right? And it really on combustion it releases a significant amount of energy, which is used for various other purposes. Now coming to its general structure, what here we can see that the carbon here is attached to 4 different hydrogen atoms via sigma bond. Now what is sigma bond? Right? Sigma bond is nothing but overlap of hybrid orbitals, and here the carbon atom is sp3 hybridized. Sp3 hybridized is nothing but orbital formed by the hybridization of 3 p orbitals plus 1 s orbital. One distinct feature of sp3 hybridized atom is they obtain a tetrahedral geometry, right? Here you can see they have a tetrahedral geometry. So they also are a feature of tetrahedral geometry is you can see that they have a bond angle of 109 degree, which means it has an equivalent structure, right? It has an equivalent structure, and when I'm talking about the bonds, it has a bond angle of 109 degree. Note that 109 degree, and that is pretty much very important when it comes to the geometry of organic compounds, be it inorganic compounds and anything else. Also here, coming to the next, you can call it a bigger elder brother of methane, or a higher homologue of ethane, or higher homologue of methane, commonly known as ethane. It is nothing but a compound containing 2 carbon atoms. Previously we had a compound containing only 1 carbon atom. Here we have compound containing 2 carbon atoms. So here it is commonly represented by the chemical formula C2H6, right? C2H6. As you can clearly see, you have 2 carbon atoms attached to 6 different hydrogen atoms, you can see. So here also the carbon has sp3 hybridization, and if you remember previously few seconds back I told you, right, the sp3 hybridized atoms have a tetrahedral geometry. So where is the tetrahedral geometry? Here is the tetrahedral geometry. You can see here is the tetrahedral geometry. Here is the tetrahedral geometry. An interesting fact here is the carbon and the carbon both are attached by a CC sigma bond, and here they have 6 CH sigma bond. Alright, CH sigma bond is between sp3c plus 1s orbital of hydrogen atom, and here you have CC bond between sp3c and sp3c, maintaining a tetrahedral geometry of 109.5 degree. And also another feature, like if you want to remember, the carbon-carbon bond length here is 154 picometers. Going to the next topic, often the chemical compounds are represented on various forms, right? On various methodologies, they are represented on the plane of paper. And the most commonly used and most widely used is the wedge and dash representation. Here you have three distinct bonds. As you can see, you have three distinct bonds, and it's basically a 3D representation of the molecule on a plane of paper. And how do you represent it? Let's come to it. You have two bonds which are on the plane of the paper. You have one bond which is above the plane of the paper. Above the plane of the paper means it comes directly towards you, perpendicular to the sheet or the paper you're writing on. And the other one here you have attached to the D is dashed bond, which is below the plane of the paper. So you can imagine it like on the plane of the paper, one is coming towards you, right? One is coming towards you. If you have the eye, one is coming towards you and the other is going back of the plane of the paper. That's how you present molecules on a piece of paper, right? So you have, as I have written, it is a solid bonds which is bond towards. These are known as the solid bonds, and these are known as the dashed bonds, right? So going to the next topic, and before going to the next topic, let me tell you, don't forget to like, share, and subscribe to GK Tricks. Here you will find amazing videos about various topics that you read in the books with some teaching by some good educators. Now coming to the topic, a distinct feature of alkenes is a bond rotation, right? So a bond rotation is somewhere where the carbon and the carbon bonds rotate, right? How do they rotate? And what factor that helps them rotate is a single bond. Here you can see a single bond. So they often rotate. Here, this comes here, this goes here, and this goes here. Similarly, this can also rotate. This goes here and this goes here. But what is the effect of rotation? We might come across this topic later in stereochemistry, where these carbon atoms often tend to change their properties based on their rotation and the bond repulsions, right? So we might come across it later. And amazing fact is it's only in alkanes where you have a C-C sigma bond, single bond, which helps them rotate. You won't find rotation, C-C sigma bond rotation, in case of alkenes where you have two bonds, or alkynes where you have three bonds, which really makes it difficult for the bond to rotate, right? So as I've already talked about, let us summarize the topics. I've talked about the rotation of alkenes, and I've talked about some most commonly used representation, which is commonly known as wedge dash representation. There are also other ways of representation, like bond line structure, where you just write like this without counting the hydrogen atom, where each point is carbon C, or other ball and stick method or space filling method. And then I talked about the structure of ethane, where you have two carbon atoms attached to each other by sigma bonds, and three hydrogen atoms attached to two carbon atoms, totally making it 6 hydrogen atoms. And then you have the structure of methane, the most important one, where it attains a unique tetrahedral geometry. As I can tell you, the tetrahedral geometry. You can see, right? It's a tetrahedral geometry where this is above and below. Like drawing it other ways, it may seem like this. Join all of them, it's like a pyramid, or commonly known as a tetrahedral, which has 4 corners. So what's the utility of all this? So So another important utility is how they affect the properties of alkenes. Coming to the properties of alkenes, which is the last topic of today, we're going to talk about few physical properties. You know, the bond rotation and all the other physical properties, the sigma bond strength, they all affect the physical properties in some or the other way. So coming to it, alkenes are usually common gases, ordinary gases, and which are odorless or colorless, right? They're odorless or colorless. That means you don't really see the gas if it's around you. It's odor and it's colorless, and it's odorless, like you can't smell. It doesn't have any distinct smell. On going to the higher carbon atoms, like higher homologues, like when you increase the carbon atoms, like when you have 15 to around 20 carbon atoms, like long chain you have, then it might, due to the intermolecular forces, they might be present in the liquid form. They might be present in the liquid form at normal room temperature, and even higher, they might even be present with solid. But this requires like a lot of carbon atoms. Coming to the melting point, you know, melting point is also due to the intermolecular forces that is present between the carbon chains. In alkenes, you have a pi bonds which contribute some great amount of intermolecular forces, and due to which they have a higher melting point, and generally higher than that of alkenes, where you have only carbon-carbon bonds and carbon-hydrogen bonds. So you generally don't have much amount of intermolecular forces, so as a result of which they have less melting point. Talking about the boiling point, you know, boiling point is the temperature at which a liquid boils. So talking about the boiling point of alkene increases, right? If boiling point of alkene increases, like if you draw a graph representing the boiling point and the number of carbon atoms, like if you have the number of carbon atoms and if you have a number of boiling point, that is a boiling point, it is often seen that the boiling point increases with an increase of carbon atoms. So what is the reason behind this? It can often be easily said that with the increase in number of carbon atoms, some amount of intermolecular strain and the van der Waals molecular forces that increases, and as a result of which the boiling point also increases. The atoms are more tightly held together and the boiling point increases. And another factor to be kept in mind is branched alkenes, right? You can see branched alkenes here have generally less boiling point than linear gel alkenes. And what is the reason due to it? Branched alkenes generally form a spherical shape, and due to sphere has the lowest amount of area, so as a result of which it has less amount of van der Waals forces, which generally depends on the surface area. So that's it. That's the reason due to which the branch carbon atoms, the branch molecules, have less boiling point. And coming to the last property that we are going to discuss about is alkenes are generally insoluble in water. Like if you take a liquid alkane, right, and try to dissolve it in water, you might really find it difficult to dissolve it in water. But take the same amount of alkane or hydrocarbon and try to dissolve it in organic solvents. And what are the organic solvents that I'm talking about? Organic solvents are generally alcohols, like ETOH, ethanol, acetone, or benzene. Right? These are the often organic solvents that you might find in a chemistry lab, that people use for dissolving many other substances. So here you might find quite ease in dissolving these alkenes in organic solvents. But similarly, you might find it, but on the same time, you might find it really difficult to dissolve these alkenes in the water. So that's it for today, guys. See you on the next video. Study and best of luck.